we define the electric field to simply be the force per unit charge at a given point. So the electric field at a point is the force at that point divided by the test charge that we place at that point. And the test charge experiences, if the test charge experiences force F, then the electric field will be F over QT. And this is a vector relationship. Now for a point charge Q, the electric field is just K times magnitude of the electric field is K times the magnitude of Q over R squared, because the force for a point charge is just K, well, if you got a point charge Q and a test charge QT, the force between the two charges will just be K times QT over R squared. That'll be the force, and if you divide by the QT, you end up with just the KQ over R squared. The vector form is, as you see here, where we take the KQ over R squared multiplied by the unit vector in the appropriate direction. I haven't used the subscripts here. Perhaps I should have, but we've done the subscripts in some detail earlier. And this being a review, we just want to kind of hit the ideas. If you don't remember about the subscripts, you need to go back, of course, and look at that. So the idea is we've got a point charge Q here, and here's some point at which we want to calculate the electric field. Well, we have some force F on this test charge. Well, okay. We've got a charge, we've got a point. We're going to put a test charge there. Got ahead of myself. And we put a test charge at this point, call the test charge QT, call the point A. Then we have a force on that test charge. The electric field is just whatever this force is divided by the test charge. As a result, if we put any charge here, we're going to be able to get the force by multiplying the charge by the electric field, because the electric field is just the force per charge. We can express the potential difference in terms of the electric field. Okay? Remember that the potential difference from A to B is the work from A to B divided by the test charge that you're moving. The test charge that requires this much work to move from A to B. And we just talked about that. Now, what's the work from A to B? Well, to get the work from point A to point B, we have to add up all the force times displacement products. Now, this is indicated as a vector product. If the force is always in the same direction as the displacement, then we could just multiply force times delta S. If the force and the displacement are not in the same direction, then we have to do this thing called a dot product that university physics students understand and others don't really need to understand at this point. But the point is we're adding up force times distance. We sum up all our force times distance contributions, and that gives us the work from A to B. Divide that by the QT, and that gives us the potential difference. Okay? F being the force on the test charge, of course. Now, that's going to be the sum of the force over the test charge dotted with delta S. And it looks like I have a little arrow over the test charge. That shouldn't be there, because test charge isn't a vector quantity, but delta S is the vector quantity. So let me put that there. Okay, bad looking arrow. It's hard to draw from this angle. Okay, that indicates that delta S is a vector. Now, the point is that QT is just a constant. Well, I'm sorry, F over QT is just the electric field. So what we have is the sum of the electric field times the displacement, or the dot product of the electric field with the displacement. And that product in the limit as your delta S's approach 0 gives us the integral of the electric field with the dotted with the displacement. The point is that the voltage from A to B can be thought of as simply the sum of the electric fields times the displacements. instead of doing force times distance, we can do electric field times distance.